Welcome to this explainer. Today, we're putting on our proverbial 1960s lab coats and stepping straight into the realm of the truly extraordinary. We are investigating a question that has absolutely captivated dreamers, scientists, and sci-fi writers for well over a century. Can humanity ever truly defy the ultimate heavyweight champion of the universe, gravity? We're going to explore the strict boundaries of physics, look for some mathematical loopholes, and unpack the historical quest to sever our cosmic tether. Okay, let's dive right in. To figure out if we can actually break the rules, we first need a roadmap. So, on the agenda today, 1. The definition of gravity. 2. The physics of attraction. 3. Relativity and negative mass. 4. Does antimatter fall up? And finally, 5. Experiments and fringe claims. All right, Section 1, the definition of gravity. When we talk about anti-gravity, we have to be incredibly precise about what we mean. Gravity is, simply put, a fundamental physical force responsible for the interactions between masses. It operates over infinite distances and dominates the macro level, like between stars and planets. But here's the wild part. It's incredibly weak. We're talking 10 to the power of negative 39 times the strength of the strong nuclear force. So what does true anti-gravity actually look like? It means actively reducing, canceling, or shielding against the effect of gravity itself. It does not mean just floating around using aerodynamic lift, or balancing forces with magnets, or using ion-propelled lifters. For it to be true anti-gravity, you literally have to turn the gravitational effect off. Moving right along to Section 2, the physics of attraction. You know, for over 400 years, brilliant minds mapped out an inescapable truth about our universe. It started back in 1543 with Copernicus realizing we revolve around the sun, followed by Kepler tracking the planets. But it was Isaac Newton in 1686 who finally gave us the actual math for attraction. From there, Henry Cavendish made the very first measurement of gravitational force in the 1790s. And then boom, 1916 hits and Albert Einstein publishes General Relativity, radically changing how we view space and time altogether. As highlighted in this presentation from the Institute for Exotic Science, this timeline isn't just a history lesson. It is a steady, relentless march toward understanding gravity's absolute iron grip on mass. Step by step, humanity measured and quantified the exact force that holds our cosmos together. Right at the core of Newton's discovery is this beautiful little mathematical anchor, an inverse squared relationship with force and distance. Basically, the further away objects are, the weaker the gravitational pull, dropping off by the square of the distance. It's a mathematically precise mechanism that defines exactly how all matter in the universe interacts. Now let's zoom out for a second. Gravity is just one of 4 fundamental forces in physics, alongside electromagnetism, the strong nuclear force, and the weak nuclear force. But here's the thing that James Clerk Maxwell noticed way back in the 19th century. Electromagnetism has opposing charges, right? Positive and negative, meaning you can have both attraction and repulsion. Gravity's charge, however, is mass energy. And based on our accepted laws, mass energy is always positive, which means gravity is always exclusively an attractive force. There's just no natural repulsive counterpart. Let's see how that holds up in Section 3, relativity and negative mass. So, what does Einstein's relativity actually have to say about this impossible concept? Einstein taught us that gravity isn't simply a magnetic-like pull. It's actually a deformation in the fabric of space-time itself. Heavy objects literally curve space, and other objects fall into that curve. So if it's just a curve in space-time, is there a theoretical loophole to bend it the other way? Well, we face a pretty fascinating scientific standoff here. Under general relativity, the math for anti-gravity actually works out, but only if something called negative mass exists to generate that repulsive force. The problem? Our standard model of particle physics, the framework that describes literally all the known building blocks of the universe, firmly states that negative mass does not exist. It's completely absent from the model. This slide brilliantly illustrates that exact theoretical bottleneck. Under accepted physical laws, true anti-gravity remains scientifically impossible without this elusive, totally hypothetical negative mass. We have the equations for how it would work, sure, but we totally lack the physical ingredients in our universe to actually make it happen. But hey, science loves a good hypothetical. If we could ever somehow isolate negative mass in a single point, the theories suggest we could build some insanely exotic tech. We're talking reactionless thrusters, stable traversable wormholes, and Alcubierre warp drives that use large negative mass to warp spacetime right in front of a ship. It sounds exactly like a retro sci-fi novel, but mathematically, it's totally fascinating, even if physically unproven. Which brings us to another thrilling atomic mystery in Section 4. Does antimatter fall up? Back in 1928, Paul Dirac was working out a quantum mechanics theory that accurately predicted the electron, but his equations spat out a second solution. He proposed this was a positively charged anti-electron. And this wasn't just on-paper math for long. It directly led to discovering the actual positron in 1932 and the antiproton in 1955. Antimatter was real. And because it was so incredibly rare, scientists naturally wondered, wait, could the gravitational interaction between regular matter and antimatter be the repulsive force we've been looking for? Does antimatter literally fall up? Well, despite the excitement, physicists quickly threw up some massive theoretical red flags. Throughout the late 50s and 60s, scientists like Philip Morrison and Leonard Schiff pointed out that if antimatter repulsed, it would completely break the conservation of energy. And as Myron Good pointed out, if particles and antiparticles responded differently to gravity, standard particle decay models, like the K-meson, would completely fall apart. So the theoretical consensus firmly rejected the idea. But in science, you have to test it to know for sure, right? The thing is, measuring gravity on antimatter is unbelievably difficult. But just recently, in 2023, scientists at CERN finally managed to compare the amount of antihydrogen escaping from the top and bottom of a vertical vacuum chamber. And the results were definitive. They officially ruled out repulsive gravity between antihydrogen and the Earth. So, unfortunately for the dreamers out there, empirical testing confirmed that antimatter definitively falls down, exactly like regular matter. That leads us to our final part, Section 5, Experiments and Fringe Claims. Because despite the strict laws of physics, the human desire to build a flying saucer is incredibly strong. Take Thomas Townsend Brown back in 1921. As a high schooler, he found that high-voltage Coolidge tubes, early X-ray tubes, seemed to change mass on a balance scale, depending on how they were turned. He combined high voltages with low conductivity materials to make devices he called gravitators. He spent decades trying to pitch these to aircraft companies and the military, coining terms like electrogravitics and the Biefeld-Brown effect. He even claimed his capacitors worked in a vacuum, proving it wasn't just air movement. Naturally, his work sparked a ton of modern conspiracy theories about classified bombers and UFOs. Fast forward a bit, and the quest takes on a more modern, high-tech flavor. In the 1990s, University of Alabama scientists Ning Li and Doug Torr theorized something called AC gravity. They suggested that applying a specific magnetic field to a superconductor could align the spins of ions to produce a tangible gravitomagnetic effect. Now, these ideas were actually compelling enough that the mainstream scientific establishment took notice. From 1996 to 2002, NASA funded the Breakthrough Propulsion Physics program, specifically to investigate these far-out space propulsion concepts. They evaluated a ton of anti-gravity-like ideas. But after rigorous study, NASA officially categorized these approaches as non-viable. They found absolutely no empirical evidence of any anti-gravity forces. So what should we take away from all this? Well, the standard model of physics, backed by centuries of math and incredibly precise modern tests like the ones at CERN, keeps our feet and our spacecraft firmly planted in the realm of classical attraction. True anti-gravity remains firmly impossible under our current understanding. But, science is a process of constant, endless discovery. If gravity is an inescapable deformation of space-time, and we know our current models of quantum mechanics and relativity still don't perfectly match up, it begs the ultimate question. Will our relentless, century-long pursuit of the impossible someday, somehow uncover a loophole we just can't see yet? Thanks for exploring this with us.